everybody, welcome to Logistic Regression. So this is going to be about like classification problems and how we deal with issues surrounding them, and how we like take our model's outputs and turn it into a classification for a given input. So yeah, what do you mean by a classification problem? It's about training a model to separate inputs into like distinct categories, which we call classes. And this is like a lot easier said than done. As like a human with like human general intelligence, we can kind of see patterns and see the boundaries between classes. But even if a machine learning model can figure out these patterns, it doesn't necessarily know how to divide or like assign inputs to classes. And there's a pretty simple way we could do this. We say that we have this in a model, and we say, okay, we train it to have discrete outputs, and then we want it to just output the number 0 if it thinks it's class 0, output the number 1 if it thinks it's class 1, etc., etc. So like you run your model, you get 1 out, and then you have this table that says, yeah, okay, 1 is this class. This is not gonna really be a good idea. It massively limits your possible functions. It limits your possible input, and it limits your possible parameters, because everything has to be discrete. And if to get a discrete output, and if the true best parameters, or like the true underlying system, isn't discrete, or like the best parameters aren't actually discrete, you're not gonna have enough quote unquote resolution to capture the true relationship. And you can multiply stuff up or whatever to increase your resolution, but generally this is pretty limiting and pretty restricting. Another way you could do it is you can map the outputs of your model onto the range 0 to like n minus 1, and then we round to the nearest integer, and then you use the integer as the class index, right? And that would work out quite okay. There's a few different ways to round to map the full range of real numbers into a limited range. We'll have a look at some in a minute. I want to have a look at one in a minute. But then the problem with the rounding is that you can't really do gradient descent with that, because they can't be differentiated. I could go through the limit as x tends to infinity of f of x plus h minus f of x, but you can kind of tell that rounding functions, they have these discontinuities, these sharp jumps that are not where there's not really a derivative there, and so you can't, gradient descent doesn't work so well for functions that involve a lot of rounding. What we could do is we could add some extra parameters to our model, and we say that they're like thresholds, and we learn them. And so you're you tell the model to learn the value of x such that if the output is bigger than x, then it's in class 1 or whatever. And that would work out. It would work okay. The thing is that this is pretty much just running doing decision tree learning and classification after you've done your entire training process for your underlying model, which is a lot of extra work, and there's probably a simpler way you could go about this. And if you wanted to use decision trees to classify things, you might as well just use the decision trees method on your input, which might not be right for your input. So we're going to simplify this down to the case of two classes, so class 0 and class 1, and we can actually use this to reframe our problem. Instead, we're saying, let's learn the probability that this input is in class 1. And this gives us a nice benefit for pretty much free, and that is we can handle uncertainty. We can have our model be unsure as to what class it is in. In our previous ideas, the model was this is definitely class 2, or this is definitely class 7. Whereas there can be a situation where your model will output 0.75, and it's okay, this is probably class 1, but it could still be class 0. And you know, and you can quantify how much, how confident it is in either direction. So like if it's 0.9, it's still maybe class 0, but it's more confident. And like the sort of mapping from 0 to n-1, we having functions that will always output 0 to 1 is going to be too limiting on our like parameters and inputs and the functions we use. So what we do is we again need to find a mapping from the full real number line to the range 0 to 1, and one that is sort of as simple and natural as possible, where we like don't lose any information. We're looking for like a bijection. And so this is where log odds comes in. So the odds is pretty much equivalent to, it is equivalent to probability. We know it's equivalent to probability because it's used all the time in sports betting and things. So we've actually got a insightful quote from the venerable Mr. William Hill here on our slide, very important. And yeah, so the odds, so the probability is like the ratio of inputs with class 1 to the ratio to all inputs, like what proportion of our inputs have class 1, whereas the odds is the ratio from our inputs with class 1 to our inputs with class 0. And this is kind of easy to, you can kind of easily tell that these are equivalent concepts. And what's important about the odds is it maps 0 to 1 to 0 to infinity. So now we have the full positive part of the real numbers accessible to us. The next thing is we also have the logarithm. And this is, like the odds, is monotonically increasing, which means that we can use it in maximization. And that maps all the positive real numbers onto the full set of real numbers. And this means that we have the mapping we need, except it's backwards. So what we have to do is we have to take the inverse of the log odds, and we get this sigmoid function. This function was just kind of given to us in AI1, and they showed us this pretty graph, and it was like, yes, this is a smooth step. This makes sense. But there are a ton of potential. There's a ton of like potential smooth step functions, and if you start with the log odds, which is, you know, not necessarily the only way to do it, but it's a pretty simple and reasonable and obvious way you could go about this. And you take the inverse and you get to this really useful sigmoid function. And you can tell that it works well because, you know, over in the negative numbers, it's 0, over in the positive numbers, it's 1. And so if your inner model outputs like a positive number, like a high positive number, it's very confident that it's class 1. If it outputs a high, extreme negative one, like sigma male, like that's the joke. It's sigmoid male because that's the joke. That's just a dumb joke. I'm sorry. I thought I was funny. And yeah. I've been thrown off now. So the sigmoid function drops out naturally from this idea of, hey, we need to map from all the real numbers to probability, and if you say, oh, we'll just take the log odds, that's the simple and, you know, easy way to do it, you get this nice sigmoid function. And so binary classification, where you then take this, where you take like a linear regression model and then plug it through the sigmoid function, this is called logistic regression. And this is what logistic regression is all about. So the idea is the class. So what we need to do now is we need to find the maximum likelihood estimation of logistic regression. And if you think about the distribution of the class of a given input, the probability that it's 1 is going to be the true function on this input. So that is, you know, true weights dot product your input put through the sigmoid function. And then the probability it's 0 is going to be the opposite of that, or, you know, 1 minus that. And so what we have is we have a Bernoulli distribution. So we say that the class of a given input, parameterized by W star, follows this by Bernoulli distribution. And if we have n independent training examples, and we want to find the parameterization that maximizes these, we just need to plug in the sigmoid, sigmoid of our input dot product our weights into this like Bernoulli distribution formula and product everything together to get the likelihood function for y output examples and x matrix input examples. It maps a parameter to this big sum of sigmoid of our this logistic function of our inputs raised to 0 raised to y, and 1 minus our inputs raised to 1 minus y. And so if y is 0, then we are going to get the right hand side, so 1 minus this sigma. And if we, as in the probability that it's not class 1, and if we have y equals 0, no, sorry, if y equals 1, then we can have the left side, which is the probability that it's class 1. What is the d in r to the d plus 1? So d is the number of dimensions of our input, and d plus 1 is because we have a bias, and so we're appending a one row to our big input matrix. Yeah, it's like the plus c in mx plus c, yes. When you're doing multivariate linear regression, you tend to have an extra parameter and slap a row of, or maybe a column, I can't remember, of ones onto your input matrix, so that you have these biases, so that it's not always traveling through 0. And so we do the same here, and then we plug through this logistic function. And so this is mostly just algebra. If we take the logarithm of the logistic, of the likelihood function, and we simplify it down, and then take the negative, we get to this slightly ridiculous loss function for logistic regression, which is subtract two sums. The first one is all the logarithm of the logistic of our input, where y is 0, sorry, where y is 1, and the logarithm is 1 minus of our logistic of our input for all y equals 0. And that's the, and you take the negative of that because it's loss and we're trying to minimize it. And here we have the gradient descent formula for the logistic regression loss function. Most of this is workings out. What actually matters is all the stuff on the bottom slide, on the bottom line of the slide. It's pretty simple. You just evaluate the model for that input, subtract y, and multiply by the input vector, and sum all that up. And you can think of this as if your output is 1 and the input and the real output is 1, or if your output is 0 and the y is 0, then you're not going to make any difference. You're not going to change the you're not going to add that input example. But if your output is 0 and the real output was 1, then you're going to subtract the input example, and if your output was 1 and the real output was 0, you're going to add the input example. So this is the loss function for logistic regression. And the other lines before that are just a lot of rearranging, a lot of applying the chain rule, and simplification. And in the end, it's pretty easy to calculate. So yeah, obviously, this isn't going to work in every case. If your outcome is binary, so if there's only two classes, then it's definitely going to work out. It doesn't quite work out the same for multiple classes. I'm going to mention at the end what you do in that case. And if your examples aren't independent, then you're not going to be able to use this formula because just a second, because you're not going to have this big product of independent Bernoulli samples, which then doesn't get turned into this sum. So if your examples are dependent, then you're going to need a much more complicated like solution. If the components of the input are too highly correlated, it's gonna also break down. I'm not exactly sure why this is. I couldn't really find anything about this online, but this is what it says in the slides. I think the idea is that if so if you're thank you, Shay. If your features are independent, then if it assumes the features are independent, then it's going to overcompensate because it's saying it's counting one feature as two effectively. If you say you have two, if you've got like x2 and x3, they're very, very correlated. Really, you should have merged them into one feature, and so the model is going to pay extra attention to x2/x3 because it's going to be counting as two features instead of one. Yeah, thank you. That makes a lot of sense. And if your sample size is too small, you're also going to have issues. There's a common rule of thumb out there on the internet that's like the number of samples you need is 10 times the number of variables times the probability of the least frequent output. So if your least frequent output is class 0, then it's going to be, and you've got 5 variables, then you've got 10 times 5 times, say, 10%, if your 90% of your output examples are class 1. And that's the number of training examples you're going to need. And then obviously, if there's not a linear relationship between input and log odds, then logistic regression is going to not work. You could use a different function. So you could say, apply the sigmoid function to a polynomial regression in a model instead. But as long as there is the inner model maps the relationship to the log odds properly, then logistic regression is going to work out. So why would we use log odds over some other function that maps from the full range of the real numbers to probability? It's because it's easier to interpret. So I'm going to have another look at a different common function that is called the probit function. I'm going to see if we can see the difference in interpretability. So probit, or phi in this case, also phi maps just like log odds. Just like the sigmoid function maps the full range of real values onto 0 to 1. And it's basically what is the probability that a standard normal distribution gets less than or equal to x. If you look at your Gaussian graph, it's the area under the tail to the left of x. And so log odds is in competition with the inverse of phi, or phi is in competition with the sigmoid function. So if we adjust an input by 1, a unit change in the input, our odds of having class 1, of the odds that our input is in class 1 is increases by e raised to the corresponding w parameter. So if we say increase x2 by 1, then our odds that it's going to be class 1 is going to increase by w2. Whereas in the probit situation, it's if we increase x2 by 1, it's the z such that the probability that a standard normal distribution is less than z equals p increases by wi. It's a lot harder to reason about, and it's a lot harder to understand what your model is actually doing under the hood, how it's making these decisions. And that's really important because normally models are black boxes, and so you can't necessarily tell if they're actually doing what you want it to do, or if they're sort of misaligned, where they're I'm getting reward for doing this thing, but that's not actually the real objective. And that's a lot easier to do when you can interpret what changes in the input are, and we sort of understand what odds are quite intuitively. and we can calculate how much the odds is increasing, and it's e to the corresponding weight. So that's pretty much everything. This one's been relatively short. There's a couple little extra fun notes. So this has been talking about the case of two input classification. There's an equivalent to the sigmoid function for multiple classes, and that is called the softmax function. It's out of scope of AI2, but it's basically if you're given a bunch of the weight for some weight for each class, it turns it into a valid probability distribution over those classes, where classes with a higher weight are more likely and classes with a lower weight are less likely, and it's effectively like sampling from that distribution is taking the maximum, but it's a bit softer. The class with the highest weight, but it's a bit softer because you might get a class with a low weight, and that's why it's called the softmax function. It's something you can look into in your own time. 3 Blue 1 Brown's video series about large language models, and the first one of those has a good introduction to it. We've been talking about maximum likelihood estimation here. Maximum a posteriori can be done in a very similar way to linear regression, where you have some prior assumptions with parameters and you multiply that by your likelihood function. If you want to know more about that, check out the Texinland lecture on MLE and MAP and things. But yeah, that's pretty much everything. And yes, it will also result in a similar regularization term. So are there any other questions that you need me to go back and clarify, or is everyone happy with what's been going on today? All good? Okay. Thank you guys so much for watching. Goodbye.